Hello everyone, welcome to my channel Hypermesh Basic to Advanced. So to have a bit of a background about my channel, so I make videos related to FEA and Hypermesh. So if you're interested in these topics, consider subscribing to my channel for regular updates. And if you're already a viewer and not subscribed, kindly consider subscribing as it motivates me to make more videos, right? Okay, so moving on to the topic of today's video. So in today's video, we'll be performing transient analysis, right? So as you can see here, I already have a meshed model on my screen here. It's an I-beam, right? I have meshed it using 2D quad elements, as you can see here. I'll just zoom in, right? Okay. So before starting the analysis, first we need to understand what is transient analysis, right? So to understand this, first we need to understand what is meant by transient, right? So transient means something that if something is changing with respect to time, then it's transient, right? So in transient analysis, what we basically do is we apply a time varying load, right? A time varying load which is varying with time, and we evaluate the stress and displacement, whatever things are there on the structure. Basically, we analyze the structure based on time varying load. So that is transient analysis. You must have heard these terms in fluid also, right? If you have studied fluid mechanics, and there will be transient flow and steady flow, right? So it's the same thing, right? It's just that this is structural analysis, right? And we are applying a transient time variable, right? So moving on. So I have the meshed model ready already. Okay. So this is an I-beam, right? If I just switch on the thickness, you can see here, right? So what we'll basically do is we'll constrain the two faces of this I-beam, the side faces, this I section, right, on both the sides, and we'll apply load, time varying load on the top flange of the I-beam, right? So I've already created the constraints. If I can just show you here. So if you can see here, I've constrained all the degrees of freedom of the nodes on this I section, right? You can see 1, 2, 3, 4, 5, 6. Constrained all the degrees of freedom, the nodes on this I section, right? And I have not constrained the degrees of freedoms of the nodes on the top flange because we'll be applying load on there. So I have not tested. I've just constrained the degrees of freedoms of the nodes on the bottom flange and the perpendicular section, right? And this side also we have done the same. Okay. So basically you have the meshed model now. You have the constraints created. Now next we need to create the material and property. So for material and property, I've used steel here. If you can see here in the white browser area, steel is by default the values are available. So I've used that only. Okay. So in case you're wondering how to create the materials and properties, you can just right click on this white browser area here, and you can go to create, and then you can go to material or property, whatever you want to create, right? Okay. So we'll be using steel as a material here. You can see these values are there, right? Then property. So I've used P shell property as this is a 2D element, right? So if I go to property here, you can see I've used P shell, and the thickness I've assigned is 2, right? So I've used 2 as the thickness of the components, right? Okay. So we have the mesh model, we have the constraint, we have the material and property. Now next word. So this is not a regular static analysis. This is a transient analysis, right? So here, as I told in the starting, here we'll apply a time varying load. Okay. So the load will be varying with time. So for that, we need to create some more load collectors. Okay, right? The first load collector we'll create will be a D area load collector, as you can see here, which I have already created. So see here, D area. I'll just switch this on, and you can see here, right? So you can see the D area load collector. It's on the top flange on all the nodes of the top flange, right? As you can see here, it's here, right? So we need to create a D area load collector, and we will select all the nodes on the top flange and apply the load collector. So in case you're wondering how to do this, so for that you can just go to analysis, right? And you can go to constraints, and you can select the nodes by face, right? You've seen, as you can see here, I've used faces. You can just select all the nodes by faces, and then I have used degree of freedom as 2, right? I have unchecked all the other degrees of freedom, and I have only checked the degree of freedom 2. That is the degree of freedom along the y-axis, right? As you can see here, degree of freedom along y-axis, right? So what we'll be doing is we'll be applying a load in the perpendicular direction, that is in the y direction. That's why I have selected the selected degree of freedom 2, right? And unchecked all other degrees of freedom. And then in the load type, you can just change this SPC to D area, right? And then you can click create. So a D area load collector will be created. Okay. So that's how you can create the D area load collector. Fine. So after this, we need to create one more load collector, that is table D1 with card image table D1, right? So what is this load collector is basically, as I told in the starting, in transient, the load is varying with time. So in this load collector, we'll basically give the data points, like how the load is varying with time, right? So if I can just show you, so here you can see table D1 num equal to 20. That means there are 20 data points here, and this table will contain the data, right? So if I can just bring it to the center, and I can just expand it a bit, as you can see, x and y, right? So at 0 the load is 0, at 1 it's 1, at 2 it's 2, 3, 4, 6 it's 6, 7, 7, 8, 8, 9, at 9 it's 8, at 10 it's 8, at 11 it's 7. So this is how the load is varying with time, right? So you can put some random values or whatever values you want, and you can just play on with these values and check what are the results. And results, it might very well be different from mine because the values will be different, right? So this is a table D1 load collector which we need to create to specify the data points, right? So next we need to create one more load collector, that is T step. So T step is basically the time step. So basically how it's moving on. So I have used n equal to 100, that is the number of time steps, that is 100, right? And the increment is 0.2, dt increment is 0.2. So basically if you just multiply n and dt, so that will give you the total number of this data points, like 0.2 into 100, it's 20, right? That's why we have 20 data points here, right? So this is time step, right? That is also created. So we have D area, table D1, and time step load collector created, right? Next we'll create R load, right? So in R load, what we do basically is the card image here is T load 1. Sorry, I have named it R load. It should be T load, fine, but it's just naming, so nothing much. So the card image, we need to create a load collector with card image T load 1, right? So in this, we have to specify the nodes which will be under the load, right? So that will be D area, right, which we have created here in the top, right, which we have selected on the top flange. So excited ID, it will be the D area, right? Then type will be load, right? And the identification table ID, the loading points, it will be table D1, which we have created 20 number of 20 loading points. 20 data points, right? Not loading points. Okay, so basically we have created D area, the place where the nodes, all the nodes where the load will be applied. We have created the data points, we have created the time step, and we have combined the D area and table D1 under T load 1, right? So next, after this, what we have to do? So after this, basically, we have constrained the body, we have applied the boundary conditions, we have created the material, we have created the properties. So next, what we need to do is we need to create the load step, right? So moving on, I already have a load step here. As you can see, I have named it transient. Okay, so transient is here. Since this is a transient analysis, I named it transient. Okay, you can name it anything you want. That's fine. So the analysis type here you will select as transient direct. You can see here, right? From there is a transient model also, but we are doing transient direct, right? We will select transient direct. Then under the SPC field, we will select the constraint which we have applied on the side face, right? This green. So we will reference this under SPC, right? Then in deload, we need to select the R load, right? And then time step, we need to select the T step, load collector, right? So this is basically what we define in the load step, right? So after this, we can just select the format in which we want to extract, right? So if you go down there, yeah, so if you go down, we have the outputs, right? Installation, failure, CMD, CMS, CS strain, CS stress. So basically what we'll basically do, we'll see the displacement and stress here. I've selected displacement, right? So format I've selected as H3D and option as all. And by the way, H3D is a output format, right? So we'll be using Optistruct solver here. Okay, so I'm using H3D format for displacement output, right? And for stress output also, we'll be using H3D format, right? Okay, so we have the load step created. So basically, we have the mesh model, we have the boundary conditions, we have the material, we have the properties, and we have the load step. Okay, so basically, we are complete in terms of starting the analysis, right? So okay, so before that, I've also created one set. If I can just hide this D area and hide this constraint. So I've created a set. You can see here. So this set constraint contains the top flange, right? So all the nodes on the top flange. So why I've created this is basically we can see how the load is varying on this nodes of the top flange. That is basically the top flange with time, right? Through the analysis. Okay. So for that I've created this set, and if you also want to do, you can do it, right? You can select all the nodes on the top flange and create a set. And to view this output, like how it's varying, basically we'll view it in a graphical format, as I'll show in the video further. So for that, you can, to view the results of this varying load on this top flange nodes time, you can just go to this analysis and control cards, right? And we can just go to global output request, right? And we can just go and select O load, right? So inside O load, we need to select the format and the ID of the set, right? SID, set ID. So format will select as H3D as usual, and set ID will select the ID of the set, right? So basically we are completing that. This is an additional step. If you want to do it, you can do it. If you don't want, it's fine. It doesn't affect the analysis. It's just extra like visualization, for better visualization, right? Okay, so meshed model is ready, constraints are, boundary conditions are there, material and properties are there, everything is there. So now moving on, so we'll perform the analysis. For that, we can go to analysis, and we can go to Optistruct. As you can see here, I'm using Optistruct. You can use any other solver if you want, but this is here, easily available, easily handy, so I'm using it, right? So we'll go to Optistruct and we'll select export options as all. It's there, run options as analysis, and then we'll click on Optistruct, right? Okay. So once you click Optistruct, a pop-up window like this will open, as you can see here, and basically this will show the progress of the run. Basically it's completed now. If you can see job completed, message for the job analysis completed, right? So this means that the analysis is completed and you can just go and view the results. So there's a results button here. If you click this, a new window will open where we can visualize the results, right? And if you want to view the output file, you can just go to view, the drop down arrow next to view, and you can just go to output file, right? And you can view the output file. But for now, we'll go to results and just visualize the results. So if you can see my screen, once you click the results, a hyperview window like this will open, right? And we can just click on apply. Okay. So as you can see on my screen, so basically it's the model is all blue. The I-beam model is all blue. That means basically there is no displacement. Okay. So why is this? We'll see. So first of all, we'll set this to transient animation mode, right? Because this is a transient analysis, right? So initially this is at t equal to 0, if you can see here, right? So the displacement is 0 at this time. So as we play this animation, you see the time is changing and you can see the displacement values are changing, right? Previously it was completely dark blue, now the color is changing, right? As you can see, it's greenish light blue kind of thing, and the legends here are also changing, right? So you can just play, okay, you see here, right? So it's again going back to full blue, right? As you can see here, the displacement is changing and it's again going to dark blue, right? So any guesses why this is happening? Okay, so if you don't know, I'll tell you sometime, right? We'll check the stress results also. So to displacement, we can just go to element stresses here, right? And we can click on apply. Okay, and then it becomes 0, 0, and we'll just play the animation. We'll see what's happening. Again, you can see the stress developing with time, how it's increasing, and then how again it's decreasing. Okay, fine. So this is how you can visualize transient analysis. And one more thing, since we extracted the loading on the top flange, the nodes on the top flange, we will just view that graph also, right? So we'll just split the window into two, and we'll just open hypergraph here. So you can just go here and we can select the graph 2D, right? And my PC is a bit slow. Okay, fine. So we have a hypergraph window here, right? So for this, we'll import we need to import the H3D file, right? So transient analysis H3D file, right? We'll open that. So what we'll see, so we want to see the displacement results, suppose. So we'll select displacement here, right? And which node should we select? So suppose we'll select node N4. We can select all nodes also, but it will be very hard to visualize, I think. So we'll select, we'll select two nodes. N2, N4. Okay, let's select 4 nodes, N1, N2, N3, N4, right? And we'll select the displacement along y-axis as the load is applied along y-axis, right? So we'll just click on apply, and as you can see, here is the graph, how the load is varying, right? How displacement is varying with respect to time, right? So x-axis is time, y is displacement. So as you can see, from 0 to 10, basically 0 to 8, the displacement is increasing, and from 8 to 10, it's almost constant, and then after that, it's decreasing, right? So what is basically happening? So I'll explain you. If you notice this here also, in this, we'll go to displacement, right? And we'll just click on play, right? So as you can see here, it's going in the graph, right? So if you see, we'll just reverse it a bit and play it slowly. So if you can see here, the displacement is slowly increasing here in the graph, and the same thing you can see in this hyperview window, right? So basically what is happening is the displacement is increasing with respect to time. It increases, then it's almost constant for 2 seconds from 8 to 10, right? And then it goes on decreasing, right? Same thing is happening. So why is this happening is basically the data points, the loading data which I have taken is, it was basically increasing from 0 to 8, and then it was constant for some time, and then it started to decrease. So the displacement is also basically following the same thing, right? The stress values are most probably going to follow the same thing. Let me just change it here, and we can see, right? But this is on the right hand side. This is not the stress graph. This is displacement graph, right? Don't mistake it for stress graph. The left hand window, we have the stress varying animation, right? Okay. So basically, this is how you perform transient analysis. Okay. So you can try it out with any other structure you want, right? And any other data points, any other loading surface where you want to load, any other location if you want to load. So you can try it out with that. You can vary the time also. You can vary the function also, right? So this is basically how you perform transient analysis. Hope you liked the video. Hope you got to learn something new. So this was all for this video. If you like this video, please like, share and subscribe, and don't forget to share the videos to anyone who needs to watch this or is interested in such topics. Thank you.